Good evening, students. In previous class, we started bottom-up parsers. In bottom-up parsers, we have two types of bottom-up parsers are there. One is LR parsers. Another one is operator precedence parser. So before we are moving to LR parsers, in previous class, we have discussed about shift reduce parsers. Shift reduce parsers. At that time, I told you, so all the LR parsers are works based on the principle that is called as shift reduce parsers. Indirectly, we can call all the LR parsers are also shift reduce parsers. In shift reduce parsers, we are having four operations mainly. One is shift, reduce, accept, and error. So we discussed some problems about shift reduce parsers in the previous class. Today I am going to move LR parsers. In bottom-up parsing, there are different kind of parsers are there. Coming to LR, there are four different kind of LR parsers are there. One is LR of 0, SLR1, LALR1, and CLR1. So in these LR parsers and operator precedence parser, LR parser having more performance criteria, which is more powerful. So you may get a theoretical question by giving any of the parsers which is more powerful, So suppose the LR0 is less powerful than SLR1, and SLR1 is less powerful than LALR1, and LALR is less powerful than CLR1. So finally, the more powerful parser in LR parsers is CLR1, more powerful parser. Sir, how can we say this is the more powerful parser, sir? As in which criteria we say the given parser is more powerful? Any grammar which accepts more number of grammars. Any parser which accepts more number of grammars. That grammar is more powerful. So here, coming to LR0, SLR1 accepts more number of grammars, and coming to LALR1, SLR accepts less number. So that's why LALR is more powerful than SLR1, and coming to LALR1 and CLR1, so CLR accepts more number of grammars. So that's why this is the order for powerful of for finding the power of LR grammars. Coming to LR grammar and operator precedence grammar. So which is more powerful? So in this, LR grammar is more powerful than operator precedence parser. LR parser is more powerful than operator precedence parser. So this is the question you may get sometimes. As a theoretically, you can get this kind of questions. So coming to our topics and problematic. So LR means, so L is the left to right scanning. And second point, R is nothing but rightmost derivation. In reverse. So in previous class, we discussed clearly why we are calling this one as a left to right scanning, because every time it scans the leftmost symbol. of the input string. That's why we are calling this one as left to right scanning, it follows left to right scan. And secondly, rightmost derivation in reverse. So bottom up parser accept the strings, it starts at leaves and moves towards root. In this process, if we write a rightmost derivation, so the reverse of the rightmost derivation and the acceptance of the string from leaves to root, both are same. That's why we are calling that one as rightmost derivation in reverse. Rightmost derivation in reverse. For this, manually, we try to find the given string is acceptable by the given grammar or not. So by finding the handles, so that is somewhat difficult. That's why we are moved to shift reduce parsers. So in this shift reduce parser, we got some problems. The problems are shift reduce problem, and reduce problem, shift reduce problem and reduce problem. These two problems may arise in shift reduce parsing technique. At that time, we are unable to, we means the algorithm, we means not ourselves, that is done by the algorithm. The algorithm unable to take or unable to choose the shift operation or reduce operation. That is the difficulty, that is the ambiguity. So in this case, that is unable to, which reduction has to perform. So that's why to overcome this problem, we are moving to another parsers in the bottom up. So those parsers are LR parsers. LR parsers. So in LR parsers, initially, we have some algorithm to accept the strings. So first I discuss the algorithm. Then after that, I move to the LR0, SLR1, LALR1, and CLR1. So for next few weeks, almost next 3 weeks, I will discuss only these 4 things. So LR0, SLR1, LALR1, CLR1. Already I told you. So 60% of the GATE syllabus covered on parsing techniques, top-down parsing and bottom-up parsing. So in that, the bottom-up parsing and in bottom-up parsing, we are having more number of different types of parsing techniques. So that's why in the next coming few classes, we will discuss about the parsing techniques, LR0, SLR1, LALR1, and CLR1. So please don't miss the classes, then only you will understand the things. If you miss the classes, it is difficult to understand the classes. So I already informed you, sir. So, okay. So today's class for first 30 minutes, for first 30 minutes. So you make some different terminology is there. So terminology already you know, LR parser you know, stack you know, input buffer you know, and parse table. So today I will introduce you a new terminology, that is parse table. So how we will form the parse table like. So here I will discuss the algorithm. So that is a little bit some different difficulties there, but I will assure you, after completion of the class, you will be able to do the problems. Definitely you will be able to do the problems, don't worry. So some theory I am going to discuss you for next 30 minutes. Please concentrate on that. So here, coming to LR parsing, we have these things, sir. This is stack. Initially, it is empty. That's why it is having $ on the top of the stack. And this is input buffer Suppose if we take a grammar, S derives AB, A derives small a, and B derives small b, and we need to accept the string AB. Here we will place the input buffer with the given string. So this is the input buffer. Input buffer holds the string we are going to accept, and stack is used to perform some push and pop operations. Initially it is empty. The dollar shows, or the top of the symbol shows, is it empty or not. And next one is LR parser. This may be LR0, this may be SLR1, or this may be LALR1, or this may be CLR1. For everything, the parser is the algorithm which reads the symbol from the input alphabet by using the stack and the parse table. It produces parse tree. Sometimes, if it is not produce a parse tree, it produces a syntax error. So initially we discussed about these things. It takes the input as a tokens from lexical analyzer. Produce the tokens and gives those tokens to the next phase, that is nothing but syntax analyzer or parser. Both are same. Here we are using LR parser, that is nothing but bottom-up parsing algorithm. So in that we are having any algorithm follows the same method. So that's why I am trying to give the algorithm first, and the procedure I will explain you for the next coming half an hour length. So okay. So here we are having 4: stack, input buffer, LR parser, and parse table. In this parse table, we may have S1, S2, so on, Sn, and the parse table having 2 parts. In LR parsing or bottom-up parsing, the parse table is having 2 parts. One is action part, another one is go-to part. Action part and go-to part. Coming to the action part, you may have shift or reduce, accept, error. In go-to part, you may have state numbers. I will explain you, sir. Every point I will clearly explain you. Don't worry. So what is shift? What is reduce? What is error? Why you are choosing this cell for reduce? Why you choose this cell for shift? For example, only I have written like that only, sir. So don't worry. So here we are having these 4, sir. So in that, the parser is the algorithm which need to produce parse tree. If it is not successful, in that case, it produces the syntax error. Because suppose if any string that is not satisfying the structure, then only it produces the syntax errors. So in previous classes, I have discussed about the syntax errors also. How can we find the syntax errors? When we say that given input having the syntax error like, so okay. Now, so we are having 4: stack, input buffer, LR parser, and parse table, and with this we will get the output, maybe parse tree. Most of the cases we will get parse tree, because in successful cases we will discuss. That's why. So in some cases that may produce syntax error. So okay. So till now we know about the stack. Stack is nothing but a data structure which is used to perform some operations. The insertion operation is called as a push, and the deletion operation is called as pop. So in this input string, the look ahead symbol, the look ahead pointer reads character by character from left to right until it reaches the end of the string. That means the end of the string is $. And coming to the LR parser, it is the algorithm. It reads the input symbol, and by using the topmost symbol of the stack, it produces the parse tree. For that, it is using parse table. For that purpose, it is using parse table. So here, now I am going to discuss when the parse table is having something, what we have to do. In the parse table, we are having four kind of things. One is reduce, another one is shift, accept, and error. So we will see. Suppose if table of the cell looks like this: T of S, comma A. Here this meaning is S means this one, and here action means A, B, C, $, and here S1, S2. These are states. These are non-terminals. These are non-terminals. Sorry, A, B. These are non-terminals. These are terminals in the given grammar, and S1, S2, S3 are states. S1, S2, S3 are states. So simply I can call this one as grammar. Simply I can call this one as grammar, and also I can call this one as DFA. DFA. Sir, in the previous classes you told you, so DFA is used in lexical analyzer for accepting the strings, and regular expressions or regular languages also used in the grammar, in the lexical analyzer. Here we use PDA for accepting the tokens and for construction of parse tree. But why you are writing DFA? Why you are writing DFA? I will explain you, sir. I will explain you why I am calling this one as DFA. I will explain you. Suppose here itself you can say, here I am having states, and here I am having some input alphabets. By starting at this state and getting this input alphabet, I am moving or I am doing some action. So for that purpose, is it acceptable or not, like that? To check, we are calling this one as DFA. If you are unable to understand this point, I will explain you again at the time of writing the parse table. Don't worry. So, but just keep it in mind, we can call it as a DFA also. We can call it as a grammar. So parse table is equivalent to DFA and grammar. So, right. So now, if we take S and A, S and A, if it is equal to accept, if it is equals to accept, that means if I take S to $, so that is producing accept. Sir, what I have to do when I will get this kind of situation? So this means the parsing is successful. This means parsing is successful. So we can directly produce the parse tree, because this is, in this situation, we can say that this is successful. And coming to the second situation, T of S comma A may be equals to error or blank, error or blank space. So in all the blank spaces, that means an error. That means an error, because there is no production to accept or shift or to do something. So that's why we can call those, these empty spaces of the table and an error case. For specification only, I have written error, sir. So all the empty spaces are comes under error. So suppose if we get T of S comma A equals to error or blank space, then we can say that parsing is unsuccessful. Parsing is unsuccessful. So parsing is unsuccessful means, so that is the, simply we can say that syntax error. Syntax error. Suppose if you get T of S comma A, this means table. In this table, suppose S row and A column. The cell is the row S and column A. So at that the action is stored as accept. In that case, we can say that the parsing is successful. Another case, suppose S comma A is equals to error or blank. In that case, we can say that that is syntax error. So these are occasionally we see, sir. So most of the cases we see. Another two cases, those are T of S comma A equals to shift J. T of S comma A equals to shift J. That means S1, S2, like. So if we see those cases, in that case, we need to do shift operation. We need to do shift operation. In the previous class, I have discussed shift reduce parsing. Shift reduce parsing. In that, I told you shift means push. Shift means push. So here I need to push. Sir, what we have to push? So here, what the symbol we read? The symbol we read is A. So first step we have to do in this case is push A into stack. Push A into stack. Then after that, we have to do one more thing, that is we need to push J into the stack. Push J into the top of the stack. Top of the stack. First we need to push the A, the symbol what we read, and next we need to push J. Sir, what is J? J means that there may be a chance S2, or there may be a chance S3, or there may be a chance S4, like shift 2, shift 3, shift 4, like the numbering will be given. So in that numbering, what is the number is there? That number we need to push into the stack. Here the number is state number. Here the number is state number. That state number we need to push it into the stack. And then finally, after pushing A and pushing J, we need to increment look ahead pointer. We need to increment the look ahead pointer. Sir, what is look ahead pointer? What is look ahead pointer? Sir, this is look ahead pointer. Look ahead pointer. So in the shift case only, we increment the look ahead pointer. In the reduce case, we don't increment the look ahead pointer. So first, what we have to do, if I get A, so if the stack is not having any non-terminal, like, so then I need to push this A into the stack. After that, I need to push the state. I need to push the state number. That may be a S1, S2, S3. So no need to push S1, S2, like, just push number. Just push number 1, 2, 3, like. We will see in the example, sir. We will see in the example. So coming to the third case, if we get T of S comma A equals to shift J, In that case, we need to push a, J, then increment look ahead symbol. Sorry, look ahead pointer. So these are the things we need to perform. And finally, suppose T of S comma A equivalent to reduce. In that case, suppose if T of S comma A equivalent to reduce, in that case, first we need to pop. First we need to perform pop operation. Pop 2 into number of B's. 2 into number of B's. Sir, what is B? I will explain you. What is B? I will explain you. Symbols, pop 2 into B symbols from stack. First we need to perform the pop operation, and secondly we need to push the non-terminal of the left hand side production. Left hand side production. And finally, we need to go to I comma A and push I into the top of the stack. Sir, what is non-terminal? What is I comma A? Go to I comma A. What is go to I comma A? So what is 2 into number of B's? What is 2 into number of B's? Sir, in the bottom-up parsing or in the top-down parsing, we do finding or detecting of the handles by replacing those handles with non-terminal. We can move from leaves to root. So in previous classes, many number of times many number of problems we saw. Suppose if there is AB and there is a grammar, S derives AB, A derives small a, B derives small b. Here A is handle because it is matching with rightmost. It is matching with substring of rightmost. Sorry, this substring is matching with the rightmost symbol of the production A derives A. So we are replacing small a with capital A here. Here A is handle. We are reducing the handle with capital A. With capital A for the process of accepting or for the process of moving to start symbol. So in the next step, so B is handle. So we are replacing B with B. Here AB is handle. We are replacing AB with yes. For the process of moving from leaves to root, we need to identify the handles. That is the process we need to do in the bottom-up parsing. For that purpose, every time we need to check what is the handle. Here the handle is A. So what are the number of symbols here? 1. What are the number of symbols here? Only 1. What are the number of symbols here in this rightmost? 2. So here B means number of symbols in the right hand side of the production. Number of symbols in the right hand side of the production. So B means the number of symbols in the right hand side production. Suppose in this case we need to pop 4 symbols because 2 into the number of symbols are 2. For that purpose, here we are reducing, or here we need to pop 2 into b number of symbols. Here we pop 2 into 1 because we are having one symbol on the right hand side, and here also only one symbol is on the right hand side. So we pop only 2 symbols. If you are unable to understand, sir, please wait for the example. There you will get the good clarity. Suppose if you are having, suppose if you are getting here itself, it is good. Suppose if you are unable to get it, so I will explain you again what is 2 into b. 2 means 2 times we need to pop, or 2 symbols we need to pop. How many number of symbols are there, sir? How can we know? So that is based on the production right hand side thing. So every production having 2. One is left hand side symbols, another one is right hand side symbols. Here b means the number of symbols in the right hand side. The number of symbols in the right hand symbols. So which production or which grammar production we are going to reduce, that in that grammar production we need to check how many number of symbols present in the right hand side. Okay, and coming to the push the non-terminal on the left hand side. So here in this case the non-terminal is yes, left hand side non-terminal is yes, sir. We are reducing AB and we are placing yes, sir. For that purpose we pop AB and we push yes, sir. Like that, sir, like that. So non-terminal is the productions left hand side symbol, productions left hand side non-terminal. So coming to go to I comma A, go to I comma A. Here go to means sorry, here I go to means this one, sir. Go to means, sorry, yeah, go to means this one, sir. Go to means this one. It may have the the table may have the states, sir. The table may have the states, sir. So go to I comma A means some state. Go to I comma A means some state. Here I means, here I means previous state, and A is the non-terminal. A is the non-terminal. So with this we can identify the state. What is the previous state of the non-terminal? Suppose S1 is the non-terminal and previous state is 2. So we need to check S2 and what is the non-terminal here? Previous state is 1 and non-terminal is 2, sir. So in that we may check 1. Here we need to check, sorry, sir, 1 minute. What I'm explaining is go to, wait, sir, sorry. Yes. So here I'm explaining you what is I, what is A. What is I, what is A. Suppose I is the previous state. Suppose previous state is 1. For example, previous state is 1. So here in this case we need to check 1 comma A in the table. 1 comma A in the table. Suppose coming to the table 1. Here it is 1 and here it is A. So we need to check what is here. What is here? Because the previous state is 1 and the non-terminal is A. The previous state and non-terminal position we need to check. Suppose if there is state 3, we need to push that particular state. Suppose if we take S1 and B, in that case, there is 1. So we need to push that 1 cell. So these are the things we need to perform. What are the things we need to do with the table? We are not constructing table. We are not constructing table, and I am not telling about the how to construct the table. So table is already existed. Table is already existed, and parser is existed. Input is existed. Stack is existed. If all are available, then how we accept the string? How we accept the string? What are the steps we need to follow? What are the steps we need to follow to accept this string? So that is the thing I am discussing, sir. So please come. We'll move with some example. Take an example. How many shift actions and reduce actions are taken by LR parser to parse the input AB by using the following grammar and parse table. If you see here, he has given input string and he has given grammar and he has given parse table. What is the problem? We need to find how many number of shift actions are performed and how many number of reduce actions are performed. Sir, what is the grammar? Right. S derives AB, the same example I am taking. A derives small a and capital B derives small b. And the parse table is given. Like this, sir. And the parse table is given like this. Okay. I0, I1, I2, I3, I4, I5. Sir, here these are states. I already told you these are states. And coming to here, A, B, dollar. This is the action table. In the LR parsing, parse table having two parts. One is the action part, another one is the go to part. Okay, come here. So here the non-terminals what we are having, A and B, sir. A and B. So with this, the elements are I0 on A, S3, I2 on B, S5, I3 on B, R2. I will explain you, sir. I will explain you everything. Don't worry. I4 on dollar R1, I5 on dollar R3. And I1 on dollar accept. I1 on accept, I0 on A, I0 on A. So sorry sir, we are having 3 non-terminals. We are having 3 non-terminals here. So this is yes, this is A. So I0 on A, that is 2, and I2 on B, I2 on B, that is 4. So finally, he has given a problem with input symbol or input string AB, and the grammar, that is S derives AB, A derives small a, capital B derives small b, and the parse table look like parse table. So these three has been given, and the problem is we need to identify how many number of shift actions are performed and how many number of reduce actions are performed. How many number of shift actions are performed and how many number of reduce actions are performed. For this, I am taking shift reduce parser. So initially in previous class we have performed this is stack and input buffer action what we are performing or parser action. Clearly, if you want to mention parser action. Initially, the stack having the symbol dollar and the given input is AB dollar. AB is the given input string and it has to end with dollar. So this is the thing, sir. So what action we have to perform? So please come once before, sir. Sir, every time the LR parser to do action on the table, with the help of table, to do action, it uses two things. One is it reads input symbol at the look ahead pointer. It reads input symbol at look ahead pointer and it checks the topmost symbol of the stack. Here there is no topmost symbol and the stack is empty. So without having non-terminal, so we cannot do the things. That's why initially we push the 0. That is nothing but the start state of the parse table. Into the stack. Now, so the top of the stack is at 0. And the input symbol is A. The top of the stack is at 0 and the input symbol is A. So T of 0, A. T of 0, A. Please come back, sir. So 0 means this one, A means this one. So 0A, this is the thing we need to perform. 0A, we need to perform S3. S means shift. Operation. So shift 3. State means state. Here the state is 3, sir. Here the state is 3. Suppose when we want to do push operation or when we get this situation, what we have to do? First we need to push A. Then we need to push the state into the stack. After that we need to increment the look ahead pointer. So here we need to push A into the stack. This is the first step. And coming to the second step, we need to push it is the existed stack and we are pushing A After that, we need to push the state. What is the state here? 3. What is the state here? 3, because he mentioned S3. He mentioned S3. So we need to push 3. We need to push 3. And then we need to increment the look ahead pointer. Initially, the look ahead pointer is at A. After incrementing one symbol, it is moving to B cell. It is moving to B cell. Now, the top of the stack is, 3. Now the top of the stack is 3. 3 of T of 3 comma. What is the input symbol? B cell. What is the input symbol? B cell. What is the input symbol here? B cell. So 3 comma B. 3 comma B. Then again go to table. What is 3B? So this is the 3B place, or this is the thing we need to do at 3 third row and B column. So we need to do reduce. What we need to reduce? R2. What we need to reduce? R2. R2 means, what is R2, sir? R2 means production 2. This is the production 1. This is the production 2. And this is the production 3. This is the production 3. Here R2 means second production. R1 means first production. R3 means third production. So here we need to reduce R2. That means A derives small a. A derives small a. At the time of reduction, what we have to do? At the time of reduction, what we have to do? We need to pop. We need to pop 2 into B. We need to pop 2 into B. Sir, here B means the right hand side symbols. How many number of symbols are there, sir? Only 1. 2 into 1, 2. So we need to pop 2 symbols. Here, these 2 symbols we need to pop. After that, the stack is, $0, and these 2 are popped. These 2 are popped based on the formula 2 into B. Here B is 1. Here B is 1. I hope you understand, sir. What is B? So here B is right hand side symbols, or the number of symbols on the right hand side production. Here in the right hand side production, we are having only one symbol. Here we are having only one symbol. That symbol we need to multiply, sir. So by multiplying 2 with 1, we will get 2. So we need to reduce, or we need to pop 2 symbols. A and 3 we popped. So after that, the second point we need to do is push the non-terminal on the left hand side. Push the non-terminal on the left hand. What is the non-terminal here? Capital A. What is the non-terminal here? Capital A. What is the non-terminal? Capital A. Then what he is telling? After that, go to I comma A, where I is the previous state. Where I is the previous state. So we will check once again. So here, before state of A is 0. Before state of A is 0. Then 0 comma A. 0 comma A. 0 comma A. What he is telling? 2. What he is telling? 2. 0 comma A. It is 2, sir. So we need to push 2. We need to push 2. So again, push 2, sir. So hope you understand. Again I will explain you this point, sir. So suppose if you are unable to understand the previous explanation, you please concentrate. So what I am telling is, here I read 3 is the topmost symbol of the stack and B in the input buffer. So in table I am checking the place of 3 comma B. In the table I am checking the place of 3 comma B. 3 comma B means R2. 3 comma B means R2. So coming to R2 means R means reduction. What we have to reduce? Which production we have to reduce? 2. Sir, how can we check? So initially we need to give the number. So from the starting to end, 1, 2, 3 like. So here S derives AB means 1, A derives capital A derives small a derives small a 2, 3. Sir, we can give the numbering like this 1, 2, 3. No sir. So we need to give in that given order only. Some order will be given for the grammar. In that order only, we need to give 1 to n number of numbering. Sorry, for productions we need to give the numbering from 1 to n. Suppose if we are having n number of productions like so. Okay, here 3 comma B means R2. R2 means we need to reduce the second production. The second production is A derives small a. A derives small a. A derives small a. We need to reduce. So for that purpose, what he is telling, for reducing, we need to pop 2 into B number of symbols. How many number of B's are there, sir? Or B? What is the number of B's, sir? Here the B number is 1 because we are having only one symbol on the right hand side of the production. We are having only one symbol on the right hand side of the production. So that's why that is 2. So we need to pop 2 symbols from the top of the stack. So here the 2 symbols are 3 and A. We popped these 2 and pushed left hand side of the non-terminal. What is the right hand side, left hand side non-terminal in the given production? A. So here we pushed A. So now, and third point we need to do there is go to I comma A. Here I means previous state. What is the previous state for A? 0. So here this means we need to go 0 comma A. Suppose if you move to the 0 comma A, 0 state and A, 0 state A, that is 2. So we'll get some state. So that state we need to push it into the stack. So like this, we'll get this one. Like that, we'll get this one. So you see. Next step. What is the top of the stack? 2. And where is the input symbol? Where is the look ahead's pointer? So the look ahead pointer is at A. Here we performed reduction. We didn't perform shift. So look ahead pointer is at B only. It is not incremented. And the top of the stack is 2. And the input symbol is B. So T of 2 comma B. Then move to the table again. So 2 comma B. 2 comma B means S5. 2 comma B means S5. So right, S5. S5 means shift 5. Shift means we need to push the symbol what we read. So here what we read? Sir. $0 A to B. B is the input symbol. So we pushed that one. After that, we need to push the state. Here the state is 5. Now we need to increment look ahead pointer. Now the look ahead pointer is at $. So next. Now the input, the top of the stack is 5, and the input symbol is at $. Then again move to the table. $5, this one. $5, this one. What he is telling? Reduce the R3. R3 means B derives small b. B derives small b. So capital B derives small b. So here, how many number of B's are there, sir? Number of B's are only 1. 2 into 1, 2. So we need to pop these 2. And we need to implement stack as $0 A2. After pop these two, we need to push the leftmost non-terminal, that is B. That is B. After that, we need to check what is the previous state. Here the previous state is 2 comma B. Check it once. 2 comma B. What is the state here, sir? The state is 4. The state is 4. So then we need to push the state 4. Go to I comma A means we need to push one more symbol, that is state. The state is 4. The input symbol is A B dollar. A B dollar. Now the topmost symbol of the stack is 4 comma the input string is or input the symbol the look ahead pointing is dollar, sir. So for that purpose we need to move to the 4 comma dollar. So what is 4 comma dollar? Yeah, here it is. 4 comma dollar means reduce R1. What is R1? S derives AB. Please concentrate here, sir. S derives AB. How many number of symbols are there in the right hand side? There are 2 symbols. So we need to multiply 2 with 2, 4. So this means we need to pop 4 symbols from the stack. Here we need to pop 4 symbols from the stack. These 4 symbols we need to pop. So now the stack is $0. If we pop A, 2, B, 4 symbols, now the stack is $0. Then after we pop the symbols, we need to push left hand side non-terminal. What is the left hand side non-terminal here? Capital S. What is the left hand side non-terminal here? Capital S. After that, we need to push. Go to I comma A. Here I is yes and previous state is 0. So move to I comma 0. Sorry. Yes comma 0 comma S. Sorry, sir. I forget to write. 0 comma S is 1, sir. 0 comma S is 1, sir. So we need to write 1. We need to write 1, sir. Now the topmost symbol of the stack is 1. And the input pointer is at look ahead pointer is at $1 comma T of 1 comma dollar. T of 1 comma dollar. Suppose if you see T of 1 comma dollar, that is accept. So here we will write accept. Here we will write accept. So this is the way we have to do accept the strings, and we need to perform the LR parsing algorithm. Everything is an algorithm, sir. Everything is an algorithm. Clear-cut steps are there. I explain you every step. I explain you every step. Suppose if T of S comma A equals to accept. Here in the previous case, T of 1 comma $K. So T of 1 comma $, equals to accept. So we can say that the parsing is successful. Suppose if it is not the case, T of S comma A is the blank or error. So in that case, we can say that is the syntax error and will come out. So these two are rarely performed, sir. These two are only rarely performed. So error is rarely performed and accept is rarely performed. More frequently performed operations are shift operation and reduce operation. Shift operation and reduce operation. In shift operation, we need to perform. First, we need to push the input symbol. First, we need to push the input symbol what we read. After that, we need to push the state. We need to push the state. So how can we know the state, sir? Suppose if it is S4, the state is 4. Suppose if it is S5, so shift S5. So the state is 5 like sir. So after that, we need to increment the look ahead pointer. In the shift operation, we perform 3 things. One is push the red symbol. After that, we need to push the state. After that, we need to increment the look ahead pointer. And coming to the reduce, we need to perform 3 steps again. Here we need to pop these many symbols. Simply these many symbols. 2 into number of b's. What is number of b? So symbols which are present on the right hand side RHS of the production. Symbols present on the RHS of the production. Suppose symbols present on the RHS of the production. Then after that, we need to, after pop the symbols, these many number of symbols, we need to push the non-terminals, the non-terminal which is present on the right hand side. Sir, how many non-terminals will present in the right hand side of the production? Sorry, left hand side of the production? Only one symbol, because this is the context-free grammar. In the context-free grammar, we have only single non-terminal on the left hand side. Only single non-terminal on the left hand side. So that non-terminal has to push into the stack. After that, we need to push I. Sir, how can we find the I? I is nothing but the previous state of I comma A. So with this, we can find the previous state. After that, we can perform these things. So here the question is, how many number of shift actions are performed? How many number of reduce actions are performed? We will check it once. Here it is shift action. So, and here it is reduce action. And here it is shift action. And here it is B, reduce action. So R3, reduce action. And here it is reduce action. So, and it is accept. So finally, there are 2 shift operations and 3 reduce operations are performed or are taken to accept the given string with the given grammar and given parse table. For the given grammar and parse table, for the given string, 2 shift operations are taken and 3 reduce operations are taken, sir. So this is the way to check how many number of tokens or how many number of actions performed. That may be simply he can ask the question as how many number of shift actions and how many number of reduce actions performed with the given LR parser. For every LR parser, we do the same algorithm or we use the same algorithm and we do the same process. So for these, it took almost 45 minutes, I think. So for the next problem, we can perform within 5 minutes. Because we know all the points. We'll check it once, sir. Take one more problem. So in the gate, you may get this kind of question, sir. How many number of shift actions and reduce actions are taken? How many number of shift actions and reduce actions are taken by LR parser LR parser to parse the given input string. The given input string, the input string is ID plus ID star ID. ID plus ID star ID. So this is the given input string. For that purpose, for that input string, so the table and grammar has been given using the following grammar and parse table for the following grammar and parse table. Suppose if you take the grammar is E derives E plus E derives E star E derives ID. E derives ID. So this is the given grammar, sir. And the parse table is given. We'll see, sir. This is action part, sir, and this is go to part. Every parse table or every LR parser table, having two. One is action, another one is go to. For this action, ID plus and star. So you just write the terminals here, sir. The terminals here are plus star ID. Sir, ID is not a two terminals. ID is the single token. So we already discussed the sequence of characters. The sequence of characters are called as tokens, and it has to satisfy some properties. The properties are keyword or constant or operator or a variable or special symbol. So it has to come under any one of these two. Sorry, these five. So this is next. In the go to, so we are having only one non-terminal, that is so here it is I0, I1, I2, I3, I4, I5, I6. The table data are I0 ID is S2 and I0 E is 1. I1 plus is S3, S4, except R3, yes, I3 is S2, I4 is S2, I5 at plus is R1, and I5 at star is S4, and I5 at dollar is R1. And coming to the I6 plus dollar and star, both are R2, sir. This is the given table, sir. Sir, in the question itself, he will give three things. One is this one, that is input string, and next one is grammar for knowing the number of productions. Production number 1, production number 2, production number 3, and to know the start symbol. So, and next one is parts table. These three things he is providing. These three things he is providing. And now we need to check. And we need to check the given input string is accepted or not. The given input string is accepted or not. Take a stack input. Sorry, sir. I will take a small piece. Stack input and actions. So initially the stack is with dollar empty. The input string is id plus id star id and with dollar. So here the top of the stack is, I already told you, initially we need to put 0 because that is the start state. That is the start state. So here t of 0 comma id, t of 0 comma id. Then go to table. So 0 comma id, the table containing S2. S2 means shift. S2 means shift. So what we need to shift? So we need to shift. We need to push. Shift means first we need to shift the symbol. What we read here? We read id. Sorry, Annie. So $0 id. After that we need to push state 2. After that we need to shift 2. So here id completed. So I'm trying to write I plus id for id star id $. The remaining part of the input string only I'm writing, sir, for the purpose of the space. For the purpose of the space I'm writing not everything. So only I'm writing this one. Now the look ahead pointer is yet plus. Now the look ahead pointer is yet plus, and the topmost symbol is 2 comma plus 2 comma plus. Go to table. So 2 plus what we have to do? We need to reduce. What we need to reduce? R3. R3 means production 3. Production 3 means E derives ID. E derives ID. E derives ID. In right hand side of the production, how many number of symbols are there, sir? Only 1. So 2 into 1, 2. Here we need to pop 2 symbols. Those are $0. These 2 symbols we need to pop. After that we need to push left hand side non-terminal. What is the left hand side non-terminal here? Is. So we need to push left hand side non-terminal, that is is. After that we need to push go to I comma a. Here E comma 0. Here E comma 0. E comma 0 means again go to 0 comma E. What is the symbol here? 1, sir. So push 1. So this is the reduction operation. After that again plus id star id $. So again the look ahead symbol is at, look ahead pointer is at plus. So now the top of the symbol is t of 1 comma plus. So again go to table. So what we have to do? So we have to check what is the next thing, and we have to check what is the thing we have to do with the help of table. The table specifies reduction. We have to do the reduction. Suppose table specifies shift, we have to perform the shift. Otherwise it may tell accept, or if it is empty it tell error. So okay, so coming to here 1 comma plus. So 1 plus that means shift 3. 1 plus, that means shift 3. So that is equals to S3. S3 means so we need to push plus, after that 3. So the stack is $0 E1 and ID. After that 3, sir. Now the input symbol is ID star ID $. So because it is completed the work of the plus. So now the look ahead pointer is at ID. Look ahead pointer is at ID. Now T of 3 comma ID. 3 of 3 comma id. 3 comma id means s2. 3 comma id means s2. So s2. S2 means shift. Again shift. So now $0 id 3. What we need to shift? id. So after that we need to shift. So 2, state 2. So this is id comma 2. After that we need to increment the look ahead pointer. That means star id $. Star id $. Now the top of the stack symbol is 2 comma the look ahead pointer is at star. The look ahead pointer is at star. So what we have to do? 2 comma star. 2 comma star means reduce 3. 3 means erase id. Erase id. In erase id, we are having only one symbol on the right hand side. Erase. Sorry, sir. Here it is id, not a d, sir. Sorry, it is id. So id means identifier, like he has given the name. So that is not a 2 symbol, sir. Don't confuse. It is only one symbol because that is token. That is token. So here we read tokens, not a symbol, not a symbols or not a characters. So the character by character has been scanned by the lexical analysis, and lexical analyzer returns tokens. Here it is token, sir. So here it is token. So we'll check. We need to reduce. How many number of symbols we need to pop? Here it is 1. So 2 into 1, that is equals to 2. 2 symbols we need to pop. These 2 symbols we need to pop, and this need to be pushed into the stack. Now the stack is $0 id 3. After that we need to insert e. What is 3? 3 is 3 e. Here it is 5. Sorry, here it is 6. 3e means 3e is 5, sir. There is 5. So we need to push 5 here. We need to push 5 here. In the reduction, we need to perform 3 things. First, we need to pop these many number of 2 into b number of symbols. After that, we need to push the non-terminal which is present on the left hand side of the production. After that, we need to push I of go to I comma a, where E is the symbol or state and I is the previous state. So E is the non-terminal and I is the previous state. So here the previous state is 3. So E comma 3 or 3 comma E, that is 5. So we pushed 5, sir. Now we are at star id $. Now 5 comma t of 5 comma star. Now t of 5 comma star. Again go to table. 5 comma star. 5 comma star means shift S4. Shift S4. So right. We'll take one more. Stack, input, and action. In stack, we are having $0 E1 ID, E1 ID, and 3E5. 3E5, sir. Now the input is star. That is already explained you. Okay. So here we are pushing star. Here we are pushing star because here it is input symbol. We read star, and the thing is S5. Yes, we need to do is S2. We'll check once, sir. We'll check it once. I5 star. Sorry, that is S4. that is S4. That means we need to push 4. We need to push 4. So this is, and input pointer is moved to another. Input pointer is moved to another symbol, that is ID dollar. Now the input pointer is at ID. Now the input pointer is at ID. Now the T of 4 comma ID. T of 4 comma ID. Then go to table. 4 comma ID. That is S2. 4 comma ID. That is S2, sir. That is S2. Again shift. So do shift operation. 0 E 1 ID 3 E 5 star 4 ID and 2, because here we are having 2, sir. So that's why that is. So now we are at dollar. 2 comma dollar. 2 comma T of 2 comma dollar. T of 2 comma dollar. 2 of 3 comma dollar means R3. Reduce R3. R3 means it derives ID. Again 2 only. So by removing these 2, we push E dollar 0 E 1 ID 3 ID 3 E 5 star and 4. After that we are placing E. And what is E comma 4? 4 comma E, that is 6. So that is 6. So we need to push 6. Now T of 6 comma dollar, because only dollar is there in the input string. 6 comma dollar. So 6 comma dollar means, so reduce 6 comma dollar, that means reduce R2. R2 means E star E. Reduce E star E. In this E star E, suppose if you see E star E, here we are having 3 symbols. 3 into 2, 6. 3 into 2, 6. So we need to pop 6 symbols. 1, 2, 3. These 6 we need to pop. Now $0 E $0 E ID is there ID? Okay. ID 3, and these all are removed, and now we are replacing with E and E comma 3. Check in E comma 3 or 3 comma E. 3 comma E, that is 5. Now we need to check T of 5 comma dollar again. 3 of 5 comma dollar. 5 comma dollar. 5 comma dollar means reduce R1. Reduce R1 means again we are having 3 symbols. Because E derives E star E. So here we need to pop. 1, 2, 3. So finally we need to pop 3 symbols. So that is these 6 these 6 will pop. So finally, we'll have dollar and E. Dollar and E. After popping, we need to push E comma 0. E comma 0 means 1. E comma 0. Okay, E comma 0 means 1, sir. E comma 0 means 1. So now the top of the symbol is 1 and the input string is dollar. 1 comma dollar. 1 comma dollar. Go to table. So 1 comma dollar is accept. 1 comma dollar is accept, sir. 1 comma dollar is accept. So this is the way to perform LR parser to check the given string is accept or not. The given string is accept or not. So by doing this, we can find the given string is accept or not. And for all the LR parsers, we perform the same thing. So up to now, we have taken 1.5 hours for doing 2 problems. But for the next classes, to do these things, we take only 5 to 10 minutes only, or within 5 minutes also we can perform. So only the thing we need to do is, here we are having 4 actions. One is shift action, second one is reduce action, and third one is accept action, or else error. In this case, what we have to perform? First, we need to push the input symbol. After that, we need to push the state J. After that, what we have to do? Increment look ahead pointer. After that, what we have to do? Increment the look ahead pointer. In the reduce, what we need to do? Pop 2 into B. 2 into number of B's. Sir, why you have given B? So here, the right hand side of non-terminals. How many number of there? To find out, one notation is given. The notation is B, sir. So you can give any notation. You can give R, you can give S, you can give X, you can give something. But the thing is here, the number of symbols present on the right hand side of the production. So that has to be multiplied with 2. So you need to pop those many number of symbols. After that, we need to push the non-terminal of LHS. In the same production, LHS non-terminal has to be pushed into the top of the stack. After that, we need to push I. What is I? That is the state. How can we find I? Go to I comma A. Here A is nothing but non-terminal. And I means previous state. Here I means previous state. So this is the thing we need to do. Suppose if every total string has been read, that means the input symbol is at the input pointer is at the look ahead pointer is at the dollar, and we are at the start symbol, then we can say that is accept. Other than these three cases, everything is an error. So if you are having any kind of doubts regarding this, to do parsing algorithm, so I didn't explain you how to draw the parse table. Here I explained you how to accept the string by doing shift and reduce actions. reduce actions. And finally, the question is, here the question is, how many number of reduce and how many number of shift actions are performed? Here it is a shift action. And here also it is a reduce. And here it is shift. And here it is shift. Here it is reduce. And here it is reduce. So 2 reduce, sorry, 3 shifts and 3 reduce. And here it is shift. And here it is reduce. And here also it is reduce. Here also it is reduce. And here it is accept. So 1, 2, 3, 4, 5, 6. 6 reduce and 4 shift operations. How many number of shift actions are performed, or how many number of shift operations are performed, and how many number of reduce operations are performed. So for that purpose, here in the given question, the shift operations are 4 and the reduce operations are 6. So you just take one question for a homework. You please do. If you are unable to do, I will explain you. So to take a write a question, sir. How many number of shift actions and reduce actions has taken to accept the string A, B, A, B, A, B, A, B, A, B for the given grammar, S derives AB, S derives AB, A derives A, B derives B. S derives AB, A derives, S derives A, S derives AB, A derives A, B derives B, sir. So that is the given grammar, and the parse table is, action go to A, B, dollar. In go to we are having S, A, B. S, A, B. So these are the terminals and these are the non-terminals. In the action part, we are having terminals, and in the go to part, we will have the non-terminals of the given grammar. I0, I1, I2, I3, I4, and I5. I5. So these are the things, sir. So the table entries are I0 on A, S3, I0 on A, S3, and I0 on here it is 2, and it is 1. I1 on accept, I2 on B, S5, I3 on B, R2, I4 on dollar, R1, I5 on dollar, that is R3. So this is the question, sir. You try to do to check how many number of shift actions are performed and how many number of reduce actions are performed. how many number of shift actions are performed and how many number of reduce actions are performed for the given input string and with the given grammar and given parse table. So with this we can find or we can check how many number of shift actions are performed and how many number of reduction actions are performed. Like that you may get the question. So you can attempt the question by knowing this algorithm and by performing these steps. Yes, sir. So here, if you come back again, we know about stack clearly. We know about input string clearly. We know the parser algorithm or LR parsing algorithm techniques, what we have to do. And now we need to know how we construct the parse table or LR parse table. How to construct the parse table. So to construct the parse table, we need to do 3 steps to construct the parse table or LR0 parse table. So here already I told you, in LR parsing we are having LR0, SLR1, LA LR1 and CLR1. So the parse table is different for LR0, SLR1 and the LALR1 and CLR1. So the construction of parse table is some slight difference is there. So I will explain you for every algorithm how to construct the parse table. For suppose if you take LR0, we can construct the parse table for LR0 parse table, LR0 table construction or parse table construction. So suppose if you take LR0 parse table, so we have to do 3 things. First we need to construct the augmented grammar. Augmented grammar for the given grammar. First thing we need to do is we need to construct the augmented grammar for the given grammar. And second thing is we need to construct LR0 items. Construct LR0 items. Here we need to construct LR0 items DFA. LR0 items DFA by using closure and goto. Sir, in the previous also I have written goto. That goto is capital goto. Now here this is small letters goto, and here in that is table. This belongs to table. Here it is a function or method. Here it is some functionality is having for this goto, and that goto is different and this goto is different. That goto is different and this goto is different. So first we need to construct the augmented grammar, or we need to write the augmented grammar for the given grammar. And second step, we need to construct the LR0 items. Sir, what is LR0 items? Explain you. I will explain you clearly. I will explain. So what is why we are calling LR0 items of DFA? So what is closure? What is goto? I will explain these three. Don't worry. So next, third thing is construct the parse table. Construct the parse table. So these 3 things we need to do to construct the LR0 table or LR0 parser table. So we'll start with some examples. S derives AB and S derives A, S derives, A derives A and B derives small b. I'm trying to take a same example for everyone because for the better understanding purpose. I'm trying to explain all the methods for the same grammar for the better understanding purpose. Right? Okay. So this is the given grammar, sir. This is the given grammar. So for this given grammar, we need to write augmented grammar. We need to write augmented grammar. Sir, what is augmented grammar? What is augmented grammar? Augmented grammar means we need to add new production for the given grammar. So the given grammar is S derives AB, A derives small a, and capital B derives small b. So this is the given grammar. For this, we need to add one more new production. The production is like S derives S. Here this S is the start symbol. This S is the start symbol. We are adding new production for the given grammar. That is nothing but augmented grammar. Sir, why we are adding new symbol? Sir, in some cases, so grammar maybe looks like this. E derives E plus N and E derives N. Here the start symbol is E. Suppose if in the bottom of parsing, if we started leaves and move to the start symbol, that is accepted. In this case, this is E and this is also E. So for which production we have to say it is accepted. So that is the problem. So for that purpose, we are taking new start symbol. With that, we are coming to this start symbol. After that, we can move forward. For this purpose, we are writing augmented grammar. So augmented grammar means simply adding new production to the given grammar is nothing but augmented grammar. So this is the augmented grammar for this one, and this is the augmented grammar for E derives E plus N and E derives N. So this is the augmented grammar for this given grammar, sir. So this is the way for construction of augmented grammar. And second one. So construction of LR0 items. Here we are trying to construct LR0 items. Sir, what is LR0 items? Sir, LR0 items means for CFG productions. What is CFG? Context free grammar. For CFG production, any CFG production having dot symbol somewhere in the right hand side, somewhere in the RHS of the production, somewhere right hand side of the production. CFG productions having dot symbol somewhere in the RHS of the production. So then we can call that is the LR0 item. That is called as LR0 item. So LR0 item means, suppose if you take any context-free grammar, suppose again I am taking this one, A derives small a and B derives small b. So with this we can write these context-free grammar, sir. S derives dot AB, comma S derives A dot B, or S derives A B dot, and S derives A derives dot A derives A dot, B derives dot B, comma B derives B dot. So these all are LR0 items. LR0 items. These all are LR0 items. For constructing these, we don't know how to write this one, how to write this one, how to write this one, how we are writing this one, this one, this one. For this, we are using closure and go to properties, or closure and go to functions. Closure and go to functions. By using closure and go to functions, we are writing the LR0 items for the given context-free grammar. If you come back, here I mentioned construct the LR0 items DFA and here he mentioned this is DFA. Here he mentioned this is DFA. Sir, in context-free grammar, why DFA? Why we are calling the DFA? So suppose these are the dot productions. These are the dot productions are LR0 items. So if you see, these all are finite. These all are finite. Suppose if you take any grammar, we can say that the LR0 items for that grammar is finite. The LR0 items for that grammar is finite. So this is the finite. Every finite set is accepted by the DFA. So that's why here we mentioned construct the LR0 items DFA. We didn't mention construct the DFA. We didn't mention the construct the DFA for the given grammar. We are constructing the DFA for LR0 items. LR0 items are finite number of items. For the finite number of symbols or finite number of items, we can construct the finite automata or deterministic finite automata. So here it is clear, I think. We are constructing LR0 items DFA. So why we are calling LR0 items DFA means the LR0 items are finite. Every time that is finite. That's why for finite set of symbols, we can construct the DFA. So in theory of computations, so you may constructed many number of finite automatas and DFAs and minimal DFAs, right? So here also he is mentioning. So for finite number of symbols, we can construct the DFA. So here we are constructing a DFA for the LR0. So LR0 items, with these LR0 items, we are constructing the parts table. That's why in the initial stage, I mentioned the parts table is nothing but DFA, because the parts table entries are LR0 items. LR0 items are the here states. So with these states only we are constructing the parts table. So that is nothing but DFA. So that's why I mentioned this is DFA. Parts table. I am calling parts table as a DFA, sir. So don't confuse. Okay. So now, sir, what is dot? So we know LR0 items. LR0 items means if any production on the right hand side, if it is having dot symbol, we can call that one as a LR0 item. Sir, what is dot? Dot is the symbol. It helps us, or it helps us means it helps to parse. It helps to the parser to detect the handles, because every parser responsibility is need to start at leaves and move to the start symbol. For that purpose, every time we need to replace it with some handle. So like that, we can move to the start symbol. For this process, the parser need to detect the handles. Handle is nothing but a substring which match with the right hand side of the production. It is the substring which match with the right hand side of the production is nothing but a handle. So every definition I clearly mentioned and I clearly explained you, sir. Handle, what is RHS, what is R&D, leftmost derivation, what is rightmost derivation, what is LHS of the production, what is the RHS of the production. So the context-free grammar type, it is in the format of alpha derives beta, where alpha is the single non-terminal and beta is the combination of terminals and non-terminals. Everything I explained you in previous classes, sir. So here dot is the symbol. It helps to the parser. to detect the handles. With these handles, we can reduce the grammar. So for that purpose, to calculate the LR0 items, we are using two things. So one is closure, another one is go to. Sir. So what is closure? Add. Closure is nothing but suppose it will be helpful to me by writing some grammar, sir. A derives B, S derives AB, A derives some B, some A, and B derives some B, sir. So suppose if I want to write a closure for any grammar, so initially I need to start at augmented grammar, sir. So I need to start with augmented grammar, that is S derives dot S. I need to start with S dash derives dot S. If any production after dot, if it is the non-terminal, please listen carefully, sir. If any production on the right hand side after dot symbol, if it is a non-terminal and it is producing anything, we need to add those production to the closure. So that's why here it is S. S is the non-terminal and S is producing this one. So S derives dot AB. And suppose then A is the dot symbol. After dot symbol we are having A is the non-terminal. That's why we need to add A derives dot A. Here small a is the terminal and it is not producing any kind of productions. So no need to add anything. So this is the closure property, or this is the closure functionality. In closure functionality, we are adding B production or S production. Suppose S derives A dot B. After dot, we are having B. Here we are adding this B production. To the closure. Why we are adding B production? Because we are having after dot there is a non-terminal B. That's why we are adding B production. So this is nothing but a closure, sir. So if you know how to find the closure and how to find the go to, so that is sufficient for constructing parse table. Augmented grammar is very easy. Just we are adding one more new production. One more new production. For finding the closure, for finding the closure, we are doing adding the B productions, if B is the non-terminal and which is immediately after dot symbol. Suppose if there is a production look like this, A dot AB. Sir, is there need to add B productions in this? No, sir, no need, sir, because after immediate dot symbol we are having terminal, that is not a non-terminal, so no need to add. So this is the thing, sir. This is closure. And coming to the go to means moving dot one position towards right. So for example, SDRS dot AB. So here we are doing go to A dot B. Here this is go to operation. Here it is go to operation. Go to operation means moving dot symbol towards RHS, or right hand side. So towards right, simply towards right. Don't say RHS, sir. Sorry. Towards right, sir. You please write towards right. Because RHS means only right hand side. Like so, we are doing right hand side only. We are putting the dot symbols and all these things in the right hand side only. So that's why moving the dot symbol towards right side. Okay, I think time up. We'll do the problems. How to construct the LR0 items, LR0 table set. In the tomorrow class, we'll write the tables. We will write the LR0 parse table by doing augmented grammar and by constructing LR0 items. For doing LR0 items, we are using closure and go to. Closure means adding the B production. If B is the immediate symbol or immediate non-terminal of dot. And go to means shifting or moving the dot symbol towards right. After finding all these, we construct the DFA, sir. After constructing the DFA, we can construct parse table. So in the next class and the tomorrow class, I will explain you how to construct the parse table by doing all these things. Thank you, sir. Thank you. I'm closing this session, sir. If you are having any doubts in the tomorrow class, you please ask. I will explain you, sir. Thank you.